Okay, so let's look at another example. This should be much shorter. We already got the background. So there is this monsoon intraseasonal oscillation. We talked about MJO in the previous podcast, and I have lots of details on intraseasonal variability and intraseasonal predictions, S2S variability and predictions elsewhere on my channel. But October to April, you have intraseasonal features propagating from west to east. So let's say they originate somewhere in the western tropical Indian Ocean. They go eastward across the Indonesian seas in various ways, enter the West Pacific, and sometimes go all the way across to the eastern Pacific onto the Atlantic and come back. We call them Madden-Julian oscillations. Lots of literature on it. Predictions happen. There is some predictability based on the waves and so on and so forth. But during May to about September, the eastward propagation gets detoured to the north over the Indian subcontinent and South China Sea, western northwestern Pacific in the deep tropics, and we call these intraseasonal oscillations that are propagating northward. Some people also use MJOs during the summer. Some people call them boreal summer intraseasonal oscillation. In the monsoon region, they are called monsoon intraseasonal oscillations or MESOs. And there are many theories for MJO and MESO and so on, and there are many theories. Generally, it means we don't know the exact answer yet. But adding to that, the detail is that we also added a theory to MESO or monsoon intraseasonal oscillation as to why things go north. Once the boreal spring and summer begin to get set up. And that's called the Central Indian Ocean mode. I won't go into the detail, but we'll read a little bit and look at one figure. Skillful prediction of Indian monsoon intraseasonal precipitation using Central Indian Ocean mode and machine learning. Okay, so Central Indian Ocean mode is something that I just mentioned. There are other theories that were proposed as well. Monsoon precipitation is dominated by intraseasonal variabilities, which we call active break periods on land, few days of rain or few weeks of rain, and then a dry spell, sometimes called mini drought or active break, right? And the skillful prediction lead time is currently less than 5 days, and this remains a great challenge for modeling and forecasting. Here we show that an intrinsic variability in the Indian Ocean, the Central Indian Ocean mode, when combined with a machine learning algorithm, can produce skillful predictions of intraseasonal precipitation over the monsoon region with a lead time of over 15 days. So 5 days to 15 days is a tremendous progress, and this is close to the theoretical predictability limit, which means probably we will not be able to extend the monsoon intraseasonal oscillation or precipitation prediction beyond this anyways. This remarkable skill improvement stems from the fact that CIO mode is dynamically related to the intraseasonal monsoon rainfall, while the data-driven ML algorithm suppresses unwanted high-frequency noise. Okay, so when you're making forecasts, if there is a lot of noise that is throwing you off track, then your predictions may not be skillful. But if machine learning can somehow sense the noise and get rid of it or get past it, then we can have skillful forecasts that go longer than the dynamical models at present. Using the CIO mode and the ML algorithm, the forecast system hybridizes physical fundamentals and versatility of data-driven algorithms. The identification of CIO mode and the verification of its significant contribution to intraseasonal predictions advance our understanding of the coupled monsoon system and also underscores the great potential of ML techniques in weather forecasts and climate predictions. So as in the previous Fuxi S2S model, here we are saying machine learning algorithm is capturing the physics and in some sense the precursors which can help us improve the dynamic models as well. Okay, so what is the plain language summary? Rainfall during the Indian summer monsoon is dominated by variations with a period of tens of days, which are referred to as the intraseasonal variabilities or active break periods, as I said. Current prediction skill of intraseasonal monsoonal rainfall is less than 5 days, and it remains a grand challenge in terms of increasing the current prediction skill and the lead time. Here we show that an intrinsic mode of variability in the Indian Ocean called the Central Indian Ocean mode, when combined with a machine learning algorithm, can produce skillful predictions of intraseasonal precipitation over the monsoon region with a lead time of over 15 days. This remarkable skill improvement stems from the fact that the CIO mode is dynamically related to intraseasonal monsoon rainfall, while data-driven ML algorithm suppresses disruptive noise with a period shorter than 10 days. Okay, noise is internal variability, and for the signal at lower frequencies longer than 10 days to emerge, you have to somehow make sure that that noise doesn't destroy your predictions. Using the CIO mode and ML algorithm, the forecast system synergizes physical fundamentals and versatility of data-driven algorithm. The identification of CIO mode and the verification of its significant contribution to intraseasonal prediction advance our understanding of the coupled monsoon system and also demonstrate the great potential of ML techniques in weather forecasts and climate predictions. So this is the CIO mode. Typically, this is where the northward so this is the Indian Ocean, Africa here, India is here. That is not visible in this graphic, but you have the maritime continent, West Pacific. This is the boiler box with 5 meters of rain per year, and this deep convection happens Walker cell on this side, the Indian Ocean section of it. So you have divergence at the top and subsidence over the Indian Ocean, and monsoon is happening also in the meantime. And shallow convection is born on the western Indian Ocean. As I said, subseasonal variabilities want to go eastward. There are warm SST anomalies that are generated at intraseasonal timescales through various processes that are related to all these. And you have convection wanting to go this way, and they are getting detoured northward, mostly into the Bay of Bengal. Call it the monsoon intraseasonal oscillation. And there is vertical wind shear and horizontal zonal wind shear. So southwesterlies are sheared in the meridional direction, and the winds change in the vertical direction, so that you have easterly shear, and you have various dynamics emerging out of that. So if you have subsidence over here, typically you have rainfall in the north, and vice versa, which is happening at intraseasonal time scale. We also call this the local Hadley cell, and so on and so forth. So there are many papers where we outline the details of these things. Jumping straight ahead to predictions, this is the correlation coefficient between TRIM rainfall, which is a satellite-based observational precipitation product, and forecasts in 2003 with a lead time of 15 days. And you are again looking at the regions of high correlation, and this is latitude, longitude, Indian Ocean is here, monsoon domain. And you are looking at all the years with correlation between TRIM and forecasts. And you can see over the Bay of Bengal, there are years when the correlations dip, but there are generally every year the skill is fairly high. I won't go into the specific years where the skill drops, but that requires that you read the paper or follow up on the background conditions that change every year. And over the Arabian Sea, there are details as to where the monsoon intraseasonal oscillations are very prominent. Bay of Bengal is the dominant region, and it's not going directly onto land, it's going on the ocean. Something happens in the northern Bay of Bengal, low pressure monsoons, low pressure depressions, low pressure systems then propagate into the core monsoon zone, and those low pressure systems also have multiple time scales, like synoptic scale of less than 10 days and low frequencies of 10 to 20 days, 30 to 60 days, and so on. So there is a relation between mesos and low pressure systems, because low pressure systems are also clustered into active periods and more scattered in the break period, and so on. So dynamically they are all important to understand. And Indian subcontinent is where you are most interested in precipitation forecasts. The skill is lower than over the oceans, because you have to translate the mesos on the oceans into rainfall over continents, which has not happened yet, but you can still get skillful predictions here. So being very brief about it, but looking at lead times and correlation coefficients over the Bay of Bengal, Arabian Sea and the Indian subcontinent, basically confirms that the CIO based machine learning versus the ensemble models, the skill persists. Here it drops off below 0.5 very quickly, less than 5 days as we said, but if you look at the machine learning, let's look at the solid line for the solid boxes in 4A. So these are the different regions we are, sorry, oops, I skipped figure 4, but yeah, I'm being bad, but nonetheless, Bay of Bengal, Arabian Sea and Indian subcontinent. Okay, so dashed lines for dash boxes in 4A and so on. And I want to leave you with the main message that the skill remains very high for 2003, a specific year where the ML was tested against dynamic models. Prediction of monsoon rainfall along with lead times in 3 regions. Solid lines with markers show the correlation coefficient between predictions and trim data using the Indian summer monsoon June to September for 2003 over the Bay of Bengal, Arabian Sea and the Indian subcontinent. The 3 regions are marked in 5A with solid boxes, so now I'm okay. These are the boxes we talked about. The dashed dotted lines in each panel show the results of the dashed dotted boxes in 5A. Okay, so that's 5A. The corresponding correlation coefficients from 11 of the S2S models are superimposed with the solid lines. Each line is for an S2S model. The multi-model average is shown with a thick line with no marker. So that's the multi-model ensemble. These are the different S2S. There is a S2S project where multiple models contribute their predictions, and this is the 11 different models with their mean. Typically we look at the mean always as a deterministic forecast, as we said before, and these are the probabilistic distributions. So the main message is that on land the skill is lower, in the sense the period is only about 10 days and then you drop off, but it's still beating the S2S dynamic models, and so you have to translate this into this, which is obviously possible again using ML, because there is always correlation between what happens in the Bay of Bengal and what happens on land through LPS or other phenomenon. Okay, so let's read the conclusions. The CIO mode is an intrinsic ocean atmosphere coupled mode which captures the physical and dynamical basis for intraseasonal monsoon rainfall prediction. The AI itself, there is a detailed description of how it is done, and as I said, I'm not on this team as an AI expert. I'm there as a dynamics expert and a process expert. So it's okay that I work with AI people to produce these predictions, and when I report these as podcasts, some people complain, hi, you are covering everything. Well, I am, because I work with a lot of people on a lot of different things, and that's how Earth system science is supposed to happen. So calm down, right? So an empirical forecast system is constructed by employing the CIO mode physics with an ML algorithm. The combination of advances in physical understanding and big data techniques is being reported more and more to lead to practical improvements in various climate predictions. So improve the models, do direct forecasts, and improve dynamic forecasts as well. The lead time is extended to about 15 days over the ocean and 10 days over the Indian subcontinent, combined with the state-of-the-art predictions of prediction of MESO and cutting-edge big data techniques such as the deep learning algorithms. A much better forecast of the monsoon interseasonal rainfall can be envisioned, especially predictions of heavy rainfall events which are reported to be increasing and are critical for managing devastating floods over the monsoon region, that can be significantly improved. Needless to say that this prediction skill must be translated to an operational forecast system with the current climate prediction models and the available precipitation data from the Global Precipitation Mission and the various reanalysis products. This is important because all the AI ML depend on data. As we saw in the previous podcast and other podcasts, the reanalysis data are often used as training for AI, but we also saw that there are issues in doing that because reanalysis products themselves are not perfect. The prediction skills of our system have spatial and interannual variations in the complex monsoon system. The intraseasonal rainfall is subject to many factors. The CIO mode, the Central Indian Ocean mode, captures a major feature among all natural factors. The dynamics of the CIO mode and its relation to intraseasonal monsoon rainfall have been diagnosed in previous studies. I'm involved in almost all of them, I think. We believe that the strong physical intimate link between the CIO mode and the intraseasonal monsoon rainfall is the basis for the enhanced prediction skill of our system. However, this relation between the CIO mode and intraseasonal rainfall varies in space and time. It's understandable that the skill is higher when and where the bond is stronger. As can be expected, the skill becomes lower when and where the association becomes weaker. Okay? Keep those in mind because there's a lot of improvements to be made. We'll be doing this operationally in the 2025 monsoon season to see how well we do in a real world situation as opposed to recreating historical forecasts. In addition, the forecasts over the Indian subcontinent seem imminently harder than those over the Bay of Bengal and the Arabian Sea. The dynamical reasons require further dedicated explorations. Nevertheless, generally, low pressure systems have an important impact on the monsoon rainfall, which is not included in our current system, since the ISVs are the focus here based on CIO. The land processes and other interactions with the atmosphere have non-negligible impacts on rainfall, such as mineral dust, vegetation, soil conditions, etc. In contrast, the CIO mode is only an ocean atmosphere coupled mode, which does not include important land properties. We suggest that this could be the physical reason that our system has a relatively low forecast skill over the Indian subcontinent. Therefore, a challenge for future studies will be to explore how to properly incorporate the land properties in the predictor or the dynamical forecast models. Although the forecast skills in figure 5a that we looked at and figure supplement 3, which I'm not showing here, are largely lower over the Indian subcontinent than they are over the oceans, the skill of our system over the Indian subcontinent is still significantly higher than the S2S models. As shown in figure 6c, which is here, I won't go back. The predicted rainfall over of our system and TRIM data have a correlation coefficient larger than 0.5 when the lead time is 10 days on land. In contrast, most S2S models drop below 0.5 when the lead time is just 2 to 3 days. The composite of S2S models do not include the correlation coefficient of, do not exceed a correlation coefficient of 0.5 even when the lead time is 1 day. Therefore, our system presents a meaningful improvement in monsoonal intraseasonal rainfall prediction even over the Indian subcontinent. So, despite all the limitations and lower skill on land, you can see that the dynamic models fall off very quickly on the subcontinent. They all do better on the oceans, even then they are much worse than the ML model. This is not to say ML model is better. This is to say we have ways of improving our physical understanding and improving predictions based on those by using AI/ML. That should be the main message. And if AI/ML can do direct forecasts in the meantime, obviously we want to use them as well. But ultimate goal should be to improve the dynamic models, because as we know from the ENSO prediction business, statistics can add a lot of value. AI/ML is much more sophisticated than just statistics. Ultimately, dynamical model guidance will be needed to maintain skillful forecasts, despite the combination of AI and ML providing improvements in model processes and forecasts. Okay, let's leave it there for now.